Tonight we're tracing a mystery that begins right above your head, where air meets light and color begins to exist. We'll see how sunlight, which seems white and simple, hides every color inside it. How the air around us bends and scatters that light until the world turns blue. And why, just beyond that thin breath of atmosphere, the same light leaves space in perfect darkness. Because what you see when you look up isn't just the sky, it's your eyes turning physics into beauty and emptiness into meaning. If these peaceful journeys help you unwind, I'd love for you to subscribe and join us again in the future. Now, take a slow breath. Let your eyes grow heavy and your curiosity drift. Together, let's step softly into the hidden world and see why the sky is blue and space is not. Chapter 1: The Colorless Light of the Sun. Picture a lazy morning. A single beam of sunlight slices through your blinds, and suddenly your kitchen is full of dancing dust. That beam looks white, pure, clean, ordinary. I used to take that for granted until I learned what white really means. The sunlight that fills your room isn't a single color at all. It's a perfect mix of every color. A rainbow folded up so tightly we think of it as one thing. That rainbow is hidden in plain sight. Think about the last time you saw a thin sliver of light hit a glass of water and split into a tiny strip of color, or when a CD threw a mini rainbow across the wall. Those little rainbows are clues. Isaac Newton famously passed sunlight through a prism and showed that white light breaks into red, orange, yellow, green, blue, indigo, and violet. The familiar RGBIV. But what's really happening is even more continuous than that. The sun emits a smooth spread of colors across the visible range, from deep reds to very energetic blues and violets. Each color corresponds to a different wavelength. Red light is long, around 700 nanometers, while blue is short, around 400 to 450 nanometers. To give that scale some feel, a nanometer is 1/1000th of a meter. Impossibly tiny, yet those tiny differences change how light behaves. Here's a simple way to feel connected to this. Stand outside and look at your shadow on a sunny day. If you squint, the shadow edges have a subtle color bleed. That's because different wavelengths are being nudged in slightly different directions by the air and particles they pass through. Or next time you see a rainbow after rain, remember it wasn't created by magic. It's the sun's white light unmasked, its component colors spread out by water droplets acting like tiny prisms. The rainbow is literal proof that white is made of many colors. Why does the sun produce that mix? The sun's surface is extremely hot, roughly 5,800 degrees Kelvin, and it emits light like a hot, glowing object across a wide band of wavelengths. That emission forms a continuous spectrum in the visible range, which our eyes blend into white when all wavelengths arrive together. It's like hearing a chord on a piano. Separate notes combine to make a single sound. Remove some notes, and the chord changes color. Block some wavelengths out of sunlight, and you'll literally notice the change in color of everything around you. Each color carries its own characteristics. Longer wavelengths like red and orange wiggle more slowly in space. Shorter wavelengths like blue and violet wiggle faster and carry more energy per photon. That energy per photon matters when light meets stuff. Different wavelengths interact differently with molecules, dust, and droplets. Blue photons, being more energetic, are more likely to be bounced around by tiny air molecules. Red photons sail through more easily. That's a hint of the drama that begins the moment sunlight meets Earth's atmosphere. And that's where the journey starts. Imagine the sun's light as a parade marching straight toward Earth. For a while, it's bright and unbothered, pure white, a balanced procession of colors. But just before the parade reaches the town square, it has to pass through a thin veil, our atmosphere. That veil is mostly transparent, but it's full of actors, oxygen and nitrogen molecules, tiny aerosols, water droplets, dust. When the sunlight touches that thin veil of air surrounding our planet, each color in the parade reacts a little differently. Some colors get nudged, some get scattered wide and far, and some continue forward almost unchanged. Think of standing in a field at dusk. The low sun sends light through more atmosphere, and suddenly the sky near the sun turns dramatic shades of red and orange. That's the red wavelengths getting through while blue light has been scattered away. Or remember seeing the sky above you in the middle of the day so boldly blue, you felt like you could dive into it. That's the shorter blue wavelengths being tossed in all directions and filling the sky. These are everyday experiences, but they're rooted in the basic fact that sunlight isn't one color. It's a spectrum, and the thin veil of air is where the different colors begin to behave differently. I like to make it even more personal. Next time you're in your car at sunrise, pull your phone camera out and take a close look at the light on the dashboard. Notice the warmth of reds and golds, the cool streaks of blues in shaded parts. That small observation is a microcosm of the big story. White sunlight contains all colors, and when it touches our atmosphere, the interaction between wavelengths and tiny particles starts to paint the sky and shape the light we see every day. So while our eyes tend to summarize the sun's output as white, that's only the first chapter. The real story is that white light is a blended chorus of wavelengths, each with its own behavior and energy, and the moment they meet, Earth's thin veil of air is where the subtle sorting begins. From here, those differences will determine whether a color keeps going, gets scattered, or bends. And that's what leads to the everyday spectacles we notice: blue skies, crimson sunsets, and the delicate rainbows that appear when light gets obediently unraveled. Chapter 2: The Invisible Sculptor, Earth's Atmosphere. Think for a moment about the last time you looked up and really noticed the sky, maybe on a morning run, waiting for the bus, or through the smeared window of a long car ride. It feels effortless. One glance, and the whole overhead dome is painted a calm, even blue. But that blue is not a property of space, or the sunlight itself so much as the way Earth's atmosphere gently sculpts the light before it reaches your eyes. Call the atmosphere an invisible sculptor. It's a soft filter of gas and dust surrounding the planet, only a few 100 kilometers thick in total. That sounds like a lot until you remember the planet itself is thousands of kilometers across. Most of what matters for the colors we see happens in the bottom few tens of kilometers, the air closest to us where we live and breathe. Up there, every molecule, every tiny speck of dust, every droplet of moisture nudges sunlight, sending pieces of it off in new directions. The sky's color is the result of that gentle, constant scattering. Now, here's a simple way to picture what's going on. Sunlight is white, because it's a mix of many colors: reds, oranges, greens, blues, each a different wavelength. The particles in the air, though, are tiny. Think really tiny. Air molecules are roughly 1,000 times smaller than the wavelengths of visible light. That mismatch in scale is crucial. When something much smaller than a beam of light gets in the way, it doesn't block the light in one big shadow. Instead, it scatters the light in every direction. That process is called Rayleigh scattering, and it's the engine behind the blue sky. Because Rayleigh scattering depends strongly on wavelength, the shorter wavelengths, blues and violets, get scattered far more than the longer reds and oranges. You can imagine the shorter waves as being easier for the tiny molecules to shake off in all directions. So when sunlight enters the atmosphere, much of the blue is thrown around the sky like confetti. So no matter where you look, some of those scattered blue photons reach your eye. The redder parts of sunlight mostly sail straight through, which is why, when you look directly at the sun midday, it looks a bit whiter or slightly yellow, because a chunk of the blue has been diverted away. That smallness of the air molecules matters in another way, too. Our eyes are more sensitive to certain colors, and the blue-violet end of the spectrum is actually scattered most strongly. But because our eyes perceive blue better than violet, and because some violet is absorbed higher up, the sky presents itself to us as a rich blue rather than a purple haze. You see this personally in subtle moments. On a clear, high-altitude day, I felt this on a mountain hike or while flying. The sky turns a deeper, more intense blue. That's because there's less air above you to scatter the sunlight, so less mixed light fills the sky, and the scattered blue that does reach you is purer. Up in a plane, the sky can look almost indigo. Conversely, when you stand in a city with a distant haze or after a smoky barbecue, the blue becomes pallid. That's because bigger particles, dust, pollution, water droplets are now in play, and they scatter light differently. Those larger particles, which might be comparable in size to the wavelength of visible light or larger, give us a different kind of scattering called my scattering. Unlike Rayleigh, my scattering doesn't favor blue over red. It scatters colors more equally. The practical result: hazy air, fog, and smog make the sky look white or gray and wash out distant colors. You can test this yourself on a humid day. Mountain outlines soften into a buttery blue-gray, losing contrast and detail because the light is being smeared by a lot of slightly bigger particles. Sunsets are where the atmosphere's sculpting turns dramatic. In the evening, sunlight has to pass through a much thicker slice of atmosphere to reach you. The light travels across a longer path near the horizon. That extra distance gives the molecules and particles more opportunities to scatter the short wavelength blues away from the direct beam. By the time the sunlight finally hits your eyes, the blue and green have been largely scattered out, leaving the longer wavelength reds and oranges. That's the reason for the classic fiery sunset. It's the leftovers after the atmosphere has filtered out the blues. Sometimes, when the air is loaded with aerosols from volcanic eruptions or wildfires, those sunsets can become unusually vivid or take on purples and deep crimsons, because the mixture and size of particles is different. Clouds, meanwhile, look white because of a different scale. Water droplets inside a cloud are much larger than gas molecules. They scatter all colors of sunlight roughly equally, so when sunlight is bounced around inside a cloud, the combined scattered light remains white. On a gray day when clouds are thick, less light gets through it all, and the sky loses its brightness. That's another way the atmosphere sculpts what we experience, not only in color, but in mood. There are smaller, almost magical effects too, ones you can notice with a few little experiments. Put on polarized sunglasses and look at the sky. Rotate your head and you'll see the intensity of the blue change. That's because Rayleigh scattered light is polarized to a degree. The atmosphere preferentially orients the electric fields of those scattered photons. Photographers use polarizing filters to deepen skies and reduce reflections. Nature gives you a built-in polarizer if you pay attention. Another everyday sign of atmospheric sculpting is the way distant mountains or buildings take on a blue veil, what artists call aerial perspective. The same scattering that makes the sky blue also scatters light coming from faraway objects, adding a bluish, softened layer between you and them. It's why landscape painters exaggerate blue for distant forms. That's exactly how your eye perceives depth in the real world. And there are moments when the atmosphere's filtering feels almost personal. Walking through a city after rain, when the air is clean and the sky is an intense, washing blue. Or watching after sunset, when the western horizon holds a lingering band of coral and mauve as the scattered reds fade slowly into night. Those are examples of the invisible sculptor at work, shaping light in ways that touch our everyday lives. So the next time you look up, remember that blue dome above you isn't a static backdrop. It's a living, shifting filter. Tiny, invisible molecules and the occasional speck of dust are continuously remixing sunlight, painting the sky and changing the way you see color, depth, and distance. With that in mind, let's move from this atmospheric palette to how surfaces on Earth, water, foliage, and buildings respond to that painted light and create the scenes we actually photograph and remember. Chapter 3. Rayleigh's Gentle Trick. Have you ever sat on a park bench, tilted your head back, and felt like the whole sky was painted in one enormous, soft blue? That gentle color isn't some cosmic choice. It's the result of a very old, very polite trick played by the air itself. In the late 1800s, a British physicist, Lord Rayleigh, noticed something simple but profound. The tiny things in the atmosphere scatter short wavelengths of light much more easily than long ones. Short wavelengths, think blue and violet, get bounced around. Longer wavelengths, like red and orange, tend to keep going. Picture sunlight as a rainbow made of different sized ripples. When those ripples hit the molecules in the air, nitrogen and oxygen mostly, the smaller, faster ripples, blue and violet, jostle the molecules more effectively and are sent off in all directions. This scattering sends blue light into your eyes, no matter which way you look. So the sky looks blue above you, rather than just in the direction of the sun. If you like numbers, Rayleigh's rule is beautiful in its simplicity. Scattering strength increases roughly with 1 divided by the wavelength to the 4th power. That sounds nerdy, but here's the intuition. Halve the wavelength and the scattering doesn't just double, it increases 16 times. That's why blue, short wavelength, is scattered far more strongly than red, long wavelength. It's almost like the air is subtly more ticklish to blue, a little nudge, and it sends blue light off like confetti. Now, you might be thinking, but wait, the sun actually emits a lot of violet, so why isn't the sky violet? 2 reasons make blue win out. First, our eyes are more sensitive to blue than to violet. Human vision favors blue-green wavelengths. Second, sunlight itself has less violet by the time it reaches us because the sun and the atmosphere filter some of it out. The result, the sky reads as blue to our eyes. This explains some everyday moments you've probably noticed. Have you ever looked up while wearing polarized sunglasses and wondered why the glare disappears and the sky goes a deeper, cleaner blue? That's Rayleigh scattering at work too. The scattered light is partially polarized, meaning its waves vibrate more in one direction than another. And polarized lenses selectively block that, reducing haze and making the sky look richer. Or think about a sunset. In the evening, the sun's light travels through a much longer slice of atmosphere to reach you. Along that extra distance, the blue and violet light gets scattered out of the direct path almost completely, leaving the longer wavelength reds and oranges to dominate the light that makes it straight to your eyes. That's why the sun looks fiery and the low sky glows with warm colors at dusk. It's the same Rayleigh trick, but stretched out across a larger slice of air. You don't have to take my word for it. You can try a simple hands-on test at home that highlights Rayleigh's effect. Fill a clear glass or jar with water, add just a drop or two of milk, and shine a flashlight through it in a dark room. Look along the side of the jar, and you'll see a bluish glow where light is scattered toward your eye. If you look through the jar toward the flashlight, the light coming straight through will look more reddish or orange. The little milk particles act like tiny atmospheric molecules. They scatter shorter wavelengths sideways and let longer wavelengths travel through. It's a mini atmosphere on your kitchen table. Rayleigh's insight also colors how we experience the sky in different places. When you're up in the mountains or on an airplane, the sky looks a much deeper, darker blue than it does at sea level. That's because there's less air above you to scatter light. Fewer collisions mean less filling in of scattered light from all directions, so the sky appears more intensely blue. Conversely, in hazy cities where bigger dust particles and pollution are present, those larger particles scatter light differently, my scattering, producing paler, washed-out skies and making the sunset colors more muted or smeared. There's something comforting about knowing the blue sky is not random. It's a quiet, mathematical dance. Tiny molecules meeting tiny wavelengths, the shorter ones getting bounced around more, and our eyes piecing together the result is blue. It connects the big visual moments in your life, childhood days at the beach, that perfect mountain vista, the dramatic orange of a campus sunset, to a simple rule discovered over a century ago. So next time you find yourself staring up, take a beat. Notice how the blue changes during the day, how it deepens after a rain, or how it fades into gold at sunset. Think about Lord Rayleigh's gentle trick, a small physics idea that turns the whole sky into a living painting you can walk under. Chapter 4. Why not violet? If violet light scatters even more than blue, why doesn't the sky look purple? I used to ask that as a kid, staring up while finger painting a mural and wondering why nature stubbornly picked one color over the other. The short answer is, physics does its part, but our eyes and the atmosphere do the rest, and they nudge the final result toward blue. Start with the physics we already talked about. Scattering gets stronger at shorter wavelengths. Violet sits on the short end of the visible spectrum, so in principle it should scatter more than blue. But there are two important filters between those scattered photons and the color we actually perceive. First, our own eyes are biased. The human retina has 3 types of cone cells that respond to different wavelength ranges: roughly long, red, medium, green, and short, blue. The short cones are not actually tuned to the very end of the spectrum where violet lives. They peak a bit into the blue. As you get closer to the ultraviolet edge, the true violet territory, the sensitivity of these cones drops off quickly. In plain language, our eyes are just not great at seeing violet. Compare it to music. Imagine the orchestra playing a very high pitch that your ears can barely hear. Even if it's loud, you won't notice it the same way as middle-range notes. Violet is that high, barely heard note for our visual system. Second, the atmosphere itself steals some of that violet before it ever reaches our eyes. The upper layers of air contain molecules, and a particularly important one is ozone, that absorbs strongly in the near ultraviolet and violet part of the spectrum. Ozone acts like a natural sunscreen for the planet, protecting us from harmful UV. A side effect is that it trims the amount of violet light scattering down in the higher atmosphere. So, although violet is scattered more efficiently per photon, fewer violet photons survive the trip to be scattered our way. Put those two effects together, and you get a simple balance. More violet scattering, but fewer violet photons to start with, and a human visual system that's not very responsive to them. The light that does reach our eyes is dominated by wavelengths where scattering is high enough and our sensitivity is strong. That sweet spot sits around what we call blue. Our brains take the inputs from all three cone types and interpret them. Because the short cone signal, blue, is the strongest relative to our sensitivity, the brain gives us a blue sky. There's another twist worth mentioning. Purple isn't a single spectral color in the way blue and green are. Purple is a mixture. It's how our brain combines red and blue signals to create the perception of purple. A single wavelength of light in the spectrum doesn't look purple, so even if more violet photons were scattered, they wouldn't automatically produce the purple sensation unless there's also the right mix of longer wavelengths. You can actually see these effects if you play with simple experiments. Take a camera with manual white balance and shoot a clear sky versus a sunset. Camera sensors often have different spectral sensitivities than our eyes and can pick up more violet, so the sky may look slightly different in photos. Or try looking through a UV blocking pair of sunglasses. They cut even more short wavelength light, and the sky can appear an unambiguous, deeper blue. So the blue sky is the compromise between physics and biology. Rayleigh scattering favors the shortest wavelengths, but the atmosphere and our eyes trim the extremes. What reaches our conscious perception is the balance point, and that balance reads unmistakably as blue. That's why, despite violet's stronger scattering, the sky refuses to be purple. Chapter 5. The Sun's Path and Golden Hours. When the sun dips closer to the horizon, everything changes. Not because the sun itself turns a different color, but because the sunlight has to travel through more of the atmosphere to reach you. Think of the atmosphere like a thicker slice of soup. When you move the spoon farther from the edge, the light passes through more air, more particles, more molecules. Shorter blue wavelengths are scattered out of the direct beam long before it reaches your eyes, leaving the longer, warmer wavelengths, reds, oranges, and golds, to take center stage. That's why dawn and dusk can look like the sky is on fire. The blue has been filtered away, and the remaining light paints the world in warm tones. If you've ever stood outside with a cup of coffee at sunrise, or lingered on a street corner as the last light fades, you've felt the effect. The angles soften, shadows grow long and elegant, and surfaces that looked flat in midday suddenly have depth and texture. Buildings catch a honeyed sheen, skin takes on a flattering warmth, and ordinary leaves glow as if backlit from within. For photographers and filmmakers, this is the golden hour, a brief window where the quality of light flatters subjects and conveys mood without heavy equipment or artificial enhancement. The science behind it is straightforward. Rayleigh scattering. Air molecules scatter shorter wavelengths, blue and violet, much more strongly than longer ones, red and orange. At noon, the sun's light passes through relatively little atmosphere, so more blue remains. The sky looks blue. But as the sun sinks, the path length increases, and those short wavelengths are scattered out of the direct line of sight, leaving the sunset palette. Tiny particles like dust, pollutants, and water droplets can amplify the reds and purples by scattering light in slightly different ways, which is why some evenings look spectacularly vivid, while others are muted. There's also a subtle difference between sunrise and sunset. Sunset colors are often richer because the air accumulates dust, pollen, and pollution during the day, adding more scattering agents. Sunrise can be crisper and cooler, especially after a clear, still night, which is why dawn sometimes feels more delicate and introspective, while dusk feels dramatic and full-bodied. Neither is better. Each has its own emotional tone, and both can transform the same scene completely. Golden hour is a loose term, not a fixed rule. As a rule of thumb, the first hour after sunrise and the last hour before sunset give you that warm, low-angle light, but the exact duration depends on latitude, season, and local topography. Near the equator, it can be short and intense. Toward the poles, it can stretch on for hours around the solstices. Clouds, of course, change everything. A thin veil can diffuse the light beautifully, while a dramatic line of clouds can catch the sun's rays and explode with color. What makes this so personally resonant is how quickly it can change your perception of a place. I've walked the same pier a dozen times, and on one afternoon it was ordinary and empty. Come back at golden hour, and it felt cinematic, like a scene written for you. It's a daily reminder that atmosphere and perspective, literally, alter our experience of the world. If you want to savor or capture golden hour, here are a few practical tips. Time it. Aim for the hour before sunset or after sunrise, but arrive 15 to 30 minutes early. The best color often happens just after the sun dips below the horizon. Use side light. When the sun is low, light skims surfaces and reveals texture. For portraits, that side light creates dimension without harsh shadows. Try backlighting for rim light. Shoot into the light to get a glowing outline around hair, leaves, or other edges. Watch clouds and reflections. Clouds can amplify color. Water mirrors can double the impact. Don't overexpose. Letting the exposure favor highlights can make colors appear deeper and more saturated. Pause and look. It's worth stepping away from your camera/phone and just experiencing the warmth on your face. Golden hour is more than a photography trick. It's the sky's daily transformation from scattered blue to filtered flame. Whether you're chasing images, taking a quiet walk, or sharing a sunset with someone, Those warm minutes invite you to notice how light shapes mood, memory, and the small miracles of ordinary places. Chapter 6. Rising Above the Blue. As you climb higher, the familiar blue starts to loosen its grip. At cruising altitude, around 10 kilometers in a jet, the sky is still a clean, saturated blue, tinged with that thin, bright layer at the horizon. But if you press your forehead to the window and really look, the blue isn't uniform. It grows deeper toward the zenith, a gradient from bright azure to a darker indigo. That gradient is the first hint of what happens when you push upward. There's less atmosphere above you to bounce sunlight in every direction. Think about the last time you flew on a clear day. The clouds below look like cotton. The sun is almost painfully bright, and the shadows on the ground are sharp. That sharpness exists because as the air thins, fewer molecules scatter the sunlight. Scattering is what turns white sunlight into blue light in all directions. It's why the sky looks like a painted dome. The process favors shorter wavelengths, the blues and violets, which is why the lower atmosphere glows blue to our eyes. But scattering depends on having stuff to scatter off, gas molecules and tiny particles. Climb high enough and there are simply fewer of those scatterers. Above about 20 kilometers, you start to notice the thinning in a different way. The blue darkens noticeably. The horizon loses that soft, low-contrast haze and becomes a crisper line. Photographers who've shot from high-altitude balloons or specialized aircraft talk about the twilight wedge, a thin band of color wrapping the planet like an atmospheric ribbon. From up there, sunrise and sunset are extended, because different layers of the atmosphere get lit or fall into Earth's shadow at different times. The colors are intense and layered. Crimson low on the horizon, then orange, then a deepening blue. It feels theatrical, like the sky is revealing its backstage mechanics. Keep going, into the stratosphere and beyond, and things change even more dramatically. Around 50 kilometers, the sky above begins to give up almost entirely on blue. The air is much thinner, and the scattering that creates that all-encompassing blue is much weaker. Light still reaches you, but it mostly comes straight from the sun, without being redirected into that diffuse sky blue glow. The effect is subtle at first, but undeniable. The blue retreats to the edges, and the patch of sky overhead grows darker and more somber. Then there's a threshold that people like to point to, the Kármán line, around 100 kilometers up. It's not a magic wall, so much as a useful marker. Below it, there's enough atmosphere to scatter visible sunlight and produce that blue dome. Above it, the air is so thin that scattering becomes negligible. When you cross that boundary in a rocket or see it from the cupola of the International Space Station, the blue dissolves into true black. And here's the part that trips a lot of people up. The black isn't because the sunlight is gone. The sun is just as bright, if not brighter. The reason the sky is black is that there is almost nothing left to spread that sunlight around. Imagine standing in an empty cathedral with a single spotlight. If the walls and dust are thick, the light scatters and the whole space glows. If the cathedral were stripped to bare stone with nothing to reflect or scatter the beam, you'd see a sharp circle of light, and everything else would appear dark. Space is that cathedral stripped bare. Sunlight pours through it in clear, unscattered beams, without the countless collisions with molecules to send photons in all directions. The background looks black, because you only see the direct light source and what it illuminates. That's why astronauts describe the sky above Earth as a deep, velvety black, even when the sun is up. Stars come into view as soon as you're above that thick, scattering layer. Not because the stars suddenly get brighter, but because daylight no longer swamps them with scattered light. And when the sun is just below the horizon for someone in low Earth orbit, you see a luminous ribbon hugging the planet. A thin blue limb, where the densest layers still scatter light, and then a stark transition to velvet black above. There are some other dramatic visual cues as well. Shadows become razor sharp. Colors on the ground pop differently because there's less atmospheric softening and fewer airborne particles to mute contrasts. Sunrises and sunsets stretch into theatrical events. From orbit, you can watch the sun dip and rise in just a few minutes, painting the atmosphere in bands of color that look almost unreal. The auroras, invisible from inside the thick of the lower atmosphere, suddenly become curtains of shimmering light, their delicate forms mapped against that black backdrop with startling clarity. On a personal level, it's a lesson in perspective. From the ground, the blue feels constant and permanent, part of the fabric of our world. Climb up and the sky teaches you how much of what you see depends on what the air does to light. The blue is not an intrinsic color of space. It's a collective effect of countless tiny interactions very near Earth's surface. Once those interactions fade, the universe's default canvas, black, reasserts itself. So, next time you're on a plane and the sky inches from azure to indigo, or when you scroll through footage of rocket ascent and see the dome darken, remember what's happening at the molecular level. Fewer molecules, less scattering, a thinning of the light's social life. The sun keeps shining, the photons keep traveling, but there's simply nobody left to pass them around. The blue gives way, and above about 100 kilometers, the sky is black, not because light disappears, but because there's almost nothing left to spread it around. Chapter 7. The Black of Space. Think for a moment about standing on a pier at noon, the sun high and harsh, and then stepping into a dark movie theater. In the theater, a single beam of light slices through the air and everything else vanishes. That contrast is exactly what space feels like, except the theater is endless, and there's no air to hold even the faintest suggestion of color between the light and the dark. On Earth, our sky is blue, because molecules in the air scatter sunlight in all directions. That scattering is a messy, friendly thing. It spreads the sun's light across the whole dome above you, so even places not pointed straight at the sun are still illuminated. When the sun slides toward the horizon, the path through the atmosphere lengthens. Blues get scattered away, and the reds remain. That's why sunsets blaze. It's the air doing the work. Remove the air, though, and you remove the scattering. In space, sunlight still shines just as brightly, but it travels in straight lines like laser beams. If you happen to be looking down one of those lines, directly at the sun, you're blinded by a pure, unfiltered glare. Turn your head an inch to the side, and suddenly you're staring into what looks like absolute black. Shadows are so black you can't see any detail inside them. Edges are razor sharp, and even tiny dust motes cast hard silhouettes. Astronauts on the moon described it as a kind of visual shock. The surface lit by white sunlight like a stage set, and beyond the set, a blackness so complete it felt like another universe. That blackness is real to our eyes, but it's not the absence of light in the cosmic sense. Space is filled with light and electromagnetic energy, just not the kinds our eyes are tuned to or arranged in the way we're used to. If your retina could sense every wavelength, you wouldn't see a single, featureless void. You would notice faint, diffuse glows from distant stars and galaxies, the warm smear of billions of unresolved suns, and the feathery scatter of cosmic dust reflecting sunlight. You'd see the Milky Way more like a ribbon of light and color, stretching overhead even in the places where it seems pitch dark to our naked eyes. You'd see the zodiacal light, that pale triangular glow sometimes visible after sunset, which comes from sunlight scattered by tiny dust particles in the plane of the solar system. You'd notice nebulae and glowing gas clouds in infrared and ultraviolet, brooding like ghosts between the points of bright starlight. A good way to picture this is to imagine a field full of fireflies. From a distance, they might look like a handful of pinpricks, but using the right camera settings, letting exposure collect light over time, you suddenly reveal a whole population of faint glimmers, patterns and motions that were invisible in a quick glance. Cameras, telescopes, and detectors do exactly that for space. They gather photons across wavelengths and over time to build images that our eyes simply can't assemble on their own. There's also the cosmic microwave background, a whisper of radiation left over from the Big Bang, bathing the universe in microwaves. It's everywhere, but it's at wavelengths trillions of times longer than visible light, and at a temperature of about 2.7 degrees above absolute zero. We don't feel it, we don't see it, but instruments tuned to those frequencies map a hum that's been traveling since the dawn of time. So, black in human terms is more like dark to human vision. The universe hums and glows and crackles in other bands. What's poetic about this is that the black of space is not emptiness as much as it's a kind of stage, a perfect velvety backdrop that lets celestial light stand out with brutal clarity. Think about looking up at the night sky from a place with zero light pollution. Stars suddenly have depth, the Milky Way's texture becomes apparent, and the darkness itself feels almost luminous because it lets those lights exist in relief. Contrast that with downtown city skies, where scattered light turns the whole dome into a washed-out gray. The contrast disappears, details vanish, and your eyes can't do the separation they need. Human experience also gives the black of space a psychological weight. We grew up with the assumption that dark means empty or dangerous. In space, dark means hidden. It means that the universe has a lot more going on than our senses can detect. That's a humbling idea, but also an exciting one. Every black patch could conceal galaxies, gas clouds, or objects radiating in frequencies we simply don't have built-in receptors for. Telescopes are like prosthetic senses that let us extend our perception and say, aha, there's a universe of color beyond the limits of the human eye. There's also an intimacy to that darkness. When you look at a night photograph taken from orbit, city lights map human activity like veins on a living organism. When you look deeper, longer exposures reveal the faint threads of starlight and glowing nebulae, reminders that the blackness isn't blank, it's layered. It's personal too. Everyone has a memory of stepping outside on a clear night and being surprised, suddenly, by the density of stars or the clarity of the Milky Way. That moment of realizing how much the eye doesn't catch is basically the same realization astronomers have every day. The black isn't absence, it's invitation. So when we say space is black, we're describing the human experience of the cosmos. sunlight that races in straight lines without air to scatter it, creating areas of intense glare and vast, absolute-looking darkness. We're also acknowledging the limits of our senses and the fact that beyond the visible lies a rich tapestry of radiation and faint light. In the next section, we'll follow that thread, looking at how instruments reveal the hidden glow and how different wavelengths paint very different pictures of the same patch of sky. Chapter 8: Our Eyes and the Illusion of Brightness. Think about the last time you lay on your back and watched clouds drift across a bright blue sky. The whole dome above you feels lit. Even when the sun is behind a cloud, you still have that sense of being bathed in light. That feeling is at the root of why space looks so wrong to our intuition. Our eyes were designed to live under a blue sky, and they assume light should come from all around. Here's the key idea. Brightness, as our brains experience it, isn't just about whether photons exist in a place. It's about photons arriving at your eyes from many directions. Scattered, diffused light filling the whole visual field. On Earth, the atmosphere does the scattering for us. Sunlight hits air molecules and tiny particles and gets sent in all directions. Shorter, bluer wavelengths scatter far more efficiently than red wavelengths. That's Rayleigh scattering in a nutshell, and it's why the daytime sky looks blue. Even when you aren't staring directly at the sun, photons from every different part of the atmosphere are entering your pupils, and your visual system interprets that as an overall bright field. Now picture outer space. The sun still pours out an enormous amount of light, but beyond the thin skin of atmosphere, there's almost nothing to scatter that light sideways. Photons travel in fairly straight lines until they hit something. A planet, a spaceship, or your eye. If you happen to look directly at the sun, don't. You get blasted with light, and everything in that small patch of your retina is extremely bright. Look anywhere else, and almost nothing is sending light into your eye from every direction. Your visual field stays dark because the sky isn't full of scattered sunlight. That's why astronauts describe the paradox. The sun is blindingly bright, stars are extremely bright points, Earth is luminous and colorful, and yet the background around these objects is a deep, velvety black. It's not that space lacks photons in an absolute sense. A lot of the electromagnetic spectrum is filled with radiation. It's that the kinds of photons and the directions they're coming from don't match the particular wiring of our eyes. Let's make that wiring concrete without getting lost in jargon. Human eyes have two main kinds of photoreceptors, cones and rods. Cones are the daytime crew. They detect color and fine detail and work best when there's a lot of light, photopic vision. Rods are for nighttime. Extremely sensitive to low light levels, but not good for color and detail, scotopic vision. Both types are tuned to work in the band of wavelengths that our atmosphere transmits well, roughly 400 to 700 nanometers. The atmosphere filters out a lot of ultraviolet and almost all of the high-energy X-rays and gamma rays, and it's nearly opaque at many infrared and microwave wavelengths that space happily carries. So evolution wired our eyes to be most sensitive where Earth's daylight tends to be. That tuning creates two important consequences. First, there is a mismatch between what's out there and what we can detect. Space is awash in infrared from warm objects, radio waves from distant sources, ultraviolet from hot plasmas, and the cosmic microwave background radiation, bathing the universe at microwave wavelengths. But our eyes are blind to all of that. Second, our perception of brightness depends on how those visible photons are distributed in the visual field. A concentrated beam or a tiny bright object can be luminous but won't light the whole scene. That's why a headlamp in a dark field lights only the area it points at. Everything else remains dark because there's no scattered light filling the space between the lamp and your surroundings. You can see the same effect in everyday life. Walk outside on a clear day and take a photo looking up without exposing the camera to the sun. The sky looks uniformly bright. Now move to a place where light is only coming from a small opening, like a tunnel with sunlight at the far end. Even if the sunlit patch is extremely bright, the tunnel itself stays much darker because the light isn't being scattered around. Or try fog or mist. Suddenly, even a distant headlight becomes a glowing haze because the water droplets scatter the light into your line of sight from many angles. The fog fills the scene with light in a way clear air doesn't. That's exactly what the atmosphere does on a planetary scale for the blue sky. There's also an important role played by the way our pupils and brains adapt. Our eyes are masters at adjusting sensitivity to handle scenes that range from moonlit darkness to a midday beach. When you step from a dark room into bright daylight, your pupils constrict and the cones take over. Your sensitivity to faint sources drops and dim stars vanish. Conversely, after a while in the dark, your pupils dilate and rods become more effective, revealing stars you couldn't see before. In space, if you're in sunlight, the exposure needed to see the brightly lit spacecraft or the planet forces your pupils and visual system into a range where faint, point-like stars are invisible. They're there, but your eyes are not tuned to detect them in that state. There's another wrinkle people sometimes think about: the cosmic microwave background, CMB. It's everywhere, filling space with radiation left over from the Big Bang. But its peak emission is at microwave wavelengths with a temperature of about 2.7 K. That means the energy is far too low and at the wrong wavelengths for our photoreceptors to notice. So space can be literally filled with radiation and yet appear pitch black to us because none of that radiation lands in the form our eyes can use. Put differently, darkness is not the same as absence of electromagnetic energy. It's the absence of electromagnetic energy within the narrow band and distribution that our eyes and brain interpret as light coming from the whole sky. Imagine standing in a room filled with invisible infrared light. Your skin might warm, instruments could register it, but your vision wouldn't change. For our perception, the only thing that makes the surroundings look bright is light in the visible band arriving from a broad range of directions. That helps explain some pleasures of stargazing from Earth that can't be replicated in orbit. Away from the atmosphere, stars don't twinkle as much, and they're razor-sharp points against black velvet. But because there's no atmosphere to scatter light, the sky behind them is far darker than the sky we see from the ground. Under a truly dark rural sky on Earth, you can still get that feeling of a vast, black backdrop studded with stars. But even then, you're seeing a sky influenced by scattering and by your eye's adaptation. On the ground at twilight, the sky glows long after the sun sets because the atmosphere continues to scatter sunlight from below the horizon into our line of sight. So when you next find yourself squinting up at a clear blue sky or trying to find a planet with binoculars, remember this: our sense of brightness is an evolved trick. It assumes a world where air scatters light, where visible wavelengths dominate, and where light comes from many directions. Space plays by different rules. It can be suffused with invisible radiation and yet look utterly black, because what our eyes need to experience brightness is not just photons, but the right photons, arriving from the right places. With that picture in mind, the way our eyes expect the sky to behave, it becomes easier to understand other strange visual effects of the cosmos. Next, we'll look at how different wavelengths reveal entirely different landscapes of the universe, and why telescopes that see outside the visible band turn blackness into a riot of structure and color. Chapter 9. The Sky on Other Worlds. Look up, really look, and you'll realize a sky is more than wallpaper. It's a signature, a fingerprint left by a world's air, its dust, its chemistry, even the star it orbits. When you travel in your mind from our familiar blue canopy to other worlds, the change isn't just visual, it's visceral. The color of a sky is the way a planet or moon breathes light, and each hue carries a story you can feel. Mars is the easiest to imagine because we've walked there with robots. During the day, Mars wears an ochre apron, a thin, dusty wash that makes the landscape feel like sepia photographs come to life. Put yourself on the crater rim. The air is gravel thin, the wind bites cold, and sunlight arrives already roughed up by billions of tiny iron oxide grains suspended in the atmosphere. Those grains scatter the sun's shorter blue wavelengths less efficiently than the long red ones, so the general light takes on that rusty butterscotch tone. It changes your sense of distance and depth. Shadows aren't stark black, but faded brown. It's like looking at the planet through a persistent, subtle Instagram filter. And then, at sunset, Mars flips the script. Around the sun, a small pale disk dropping toward the horizon, there's a surprising splash of blue. This isn't some poetic exception. It's physics. The Martian dust prefers to throw light forward, so when the sun is low, the scattering enhances the bluish hues near the sunbed, while the rest of the sky keeps its rusty glow. If you were there, watching that blue halo appear and then slip away, it would feel intimate and rare, like catching the brief, honest face of a stranger. Titan, Saturn's largest moon, offers a more immersive change. Imagine stepping out under a heavy, hazy orange sky where the light is soft and the world is muffled. Titan's atmosphere is dense, thicker than Earth's, yet cold and rich in nitrogen and methane. Sunlight streaming through this mixture sets off a chemistry that makes its own pigments. Complex organic aerosols called tholins form in the upper atmosphere and drift down like a perpetual autumn fog. These particles are larger and more jagged than the gas molecules that color our sky, so they scatter light differently, favoring warm amber tones. Daylight there feels filtered, like the sun is trying to get through a perpetual golden curtain. If you put your face to Titan's wind, if you could stand there without a suit, the air might smell of hydrocarbons, sharp and organic. Sound would be dampened by the thick air. The orange hush would make ordinary things feel secretive, like every silhouette is moving through a storybook illustration. And because Titan's haze scatters sunlight in a complex way, the quality of twilight is elongated. Sunsets last and fold slowly. That slowness changes perception. Minutes stretch. silence feels deeper. Now jump far out past the frozen edges of the solar system to Neptune, and you get a different lesson in how atmosphere sculpts color. Neptune's deep, dynamic atmosphere is mainly hydrogen and helium, with traces of methane. Methane molecules are ruthless about one thing: they gobble up red and yellow wavelengths. What's left are cool blues and deep indigos, the palette we associate with Neptune. But unlike Earth's bright, airy blue, Neptune's color has depth. Think of it as the difference between a robin's egg bowl and a glass of indigo ink. The planet's sky fades into a rich, surreal indigo as you peer upward, hinting at layers and pressure and storms hidden beneath. If you could hover in a probe above Neptune's upper clouds, the sun would be a distant, brilliant star, stark against a sea of deep blue that feels both alien and oddly elemental. These colors, rusty ochre on Mars, hazy orange on Titan, indigo on Neptune, are all the result of the same fundamental concept: how particles and gases scatter and absorb light. On Earth, tiny gas molecules scatter shorter wavelengths more efficiently, Rayleigh scattering, so the sky is blue. When particles are larger, dust, aerosols, or droplets, they scatter light more equally, scattering, producing whites, grays, or those warm, dusty tones. When a gas selectively absorbs certain wavelengths, like methane trimming away reds on Neptune, you're left with the spectral leftovers that define the sky's hue. But there's another variable people forget: the star. Sky color depends on the light you start with. Around a red dwarf, the sunlight is shifted toward the red end of the spectrum, so even Earth-like scattering would yield a different cast. Imagine standing under a lavender dusky sky, because the sunlight itself leans toward crimson. That means alien skies may deceive our sense of natural color, because the palette is set not just by the planet, but by the star it orbits. Beyond the technical, there's a human part to this. Color anchors memory. The blue of our sky is the background of childhood summers, of seeing a storm roll in, of simple directions like, look up. If you stood under Titan's steady orange haze, the world would rewrite those anchors. Your memories of light and warmth would be recoded. A Martian sunset with its sudden blue halo would feel like a private secret between you and the planet, a tiny tear in the film of the familiar. Neptune's indigo would make you feel small in a different way, not just tiny, but suspended in an ocean of color that hints at immense pressures and processes. Finally, remember that these skies are records. They tell scientists what a world is made of, how it evolved, whether it could support chemistry that led to life. When we look at a sky's color, we're reading a planet's biography in real time. Its geology, its chemistry, its relationship to its star. So the next time you imagine walking across alien ground, don't just picture the terrain. Picture the light, how it comes, how it's shaped, what it makes you feel. Each color is an answer, and knowing how to read it is how we learn to listen to other worlds. Chapter 10: Why We See Beauty in Blue. So why do we find blue so quietly beautiful? Part of it is physical, but part of it is a kind of emotional bookkeeping our minds do without us noticing. Think about the last time you stopped to look up, maybe on a park bench, or half asleep with your head on a pillow near an open window. There's a moment when the blue takes over the edges of your vision and the rest of the world slows. It's not loud like red or demanding like neon. Blue feels like a choice the sky makes to give us space. On a simple level, there's a balance at play. Blue sits between extremes. It's heated by sunlight yet toned down by distance. It's bright without shouting. It contains light, but not the harshness of direct glare. We're living inside a scattering show. Sunlight hits molecules in the air, and the shorter blue wavelengths get bounced around into every direction, wrapping us in a soft blue glow. That scattering is what creates the illusion of a dome. We look up and see color above us, not because there's paint up there, but because the air itself turns the light into a color field. There's something reassuring about being enclosed in that gentle, almost accidental canopy. That balance you feel is mirrored in how we emotionally respond to blue. It straddles opposites, energy and calm. Consider water, moving, alive, reflective, and then think of a clear sky. Still, expansive, infinite. Both are blue, and both convey different kinds of safety. Energy doesn't always mean agitation. It can mean potential. Calm doesn't always mean numbness. It can mean clarity. Blue gives you permission to hold both at once. It tells your nervous system that danger isn't immediate, even when the day is full of things to do. There's also a spatial reason blue feels endless. Colors at longer wavelengths, reds and oranges, tend to feel close. Blues recede. That visual receding creates a sense of distance that feels generous. When we look at blue, our eyes and mind interpret depth and openness. It's why a room painted blue can feel larger, why oceans and skies give us that inhale we didn't know we needed. That sense of above versus below matters emotionally. The blue dome overhead becomes a reference point. It's limitless and impartial. Below it, life unfolds. Messy, urgent, immediate. Above it, there's a patient continuity. We also carry personal histories in our color responses. Maybe your first summer memory is running with bare feet on a lawn and glancing up to a sky so deep you could disappear into it. Maybe blue is the color of the ocean your family took you to, a place of salt and laughter. Those moments layer onto the biological effects. Blue light can regulate circadian rhythms and influence mood. When you look at the sky, your body recognizes patterns it has learned to trust. Daytime, wakefulness, possibility. The experience is both modern science and ancient habit. Another thing that makes blue feel right is how it frames contrast. Against the green of trees, the brown of earth, the human skin tones, and the bright colors of clothing, blue is the neutral companion that doesn't compete. It sets a stage. When you stand in that stage, your problems keep their edges, but they don't dominate the whole view. That's why photographers chase blue hours, and why designers use blue to reduce visual noise. It gives other elements room to exist without overwhelming them. Finally, there's a quiet philosophical side. The blue sky is a reminder of interdependence. Light, air, the molecules we can't see. We're wrapped in something essential and invisible. There's a humbling comfort in that. The air that scatters blue light is the same air we breathe, the same air that has carried pollen, songs, and even trouble across distances. The sky is both a mirror of physics and a soft metaphor for how small acts, like a photon bouncing off a molecule, create the larger phenomena we take for granted. So when you next find yourself pausing to look up, notice how the blue holds your gaze. Notice how it balances brightness and softness, presence and distance, motion and stillness. It's an everyday spectacle. Scattered sunlight, an unpainted dome, a lived-in blue that keeps giving. And because it's woven into both our bodies and our stories, it never really feels like mere color. It feels like a companion. Now you know, the sky is blue because air dances with light, and space is black because silence holds it still. Wherever you are tonight, look up. Imagine invisible light passing through you, scattering softly, keeping your world glowing in blue. If this moved you, tell me where you watched from and subscribe to keep exploring together. I love hearing where you watch from. Your sky becomes part of this channel. Good night, and keep looking up, and keep